Yesterday we were discussing a very important topic of solutions. So today we are going to discuss another colligative property, that is depression in freezing point and osmosis. Okay, so let's start the lecture. So in the previous lecture we have done a very important concept of relative lowering in vapor pressure, right? So we have already said that when we are dissolving a non-volatile solute to a solvent, the vapor pressure of the solution would decrease, right? So we derived a formula which is P naught minus Ps upon P naught, that was equal to the mole fraction of solute, right? So this was the formula which we used in the previous lecture and we did some problem solving on this, okay? So now just if you look at this expression, we can also write this as number of moles of solute upon number of moles of solute plus number of moles of solvent is equal to P naught minus Ps upon P naught, okay? So there is a little correction, I think I have written it wrong yesterday, so by mistake I think it went wrong. So we are taking the reciprocal of this, so when we are taking the reciprocal of this, this would become the number of moles of solute plus number of moles of solvent divided by number of moles of solute, okay? So I think in the previous lecture I have written it solvent over here, so it was my mistake, so just make that necessary correction so that it does not confuses you, okay? So just what we have done, we have taken the reciprocal of this expression, okay? So when we have taken the reciprocal of this solution, so this would become this, okay? So we can rewrite this as 1 plus number of moles of solvent upon number of moles of solute equals to P naught upon P naught minus Ps, okay? So we can write this as number of moles of solvent upon number of moles of solute as P naught upon P naught minus Ps minus 1. So when you solve this, this becomes number of moles of solvent upon number of moles of solute is equal to Ps upon P naught minus Ps. So this was the correction that you should make in your notes, okay? By mistake, when I took the reciprocal, I wrote this as number of moles of solvent over there. So this is the correction that you should take care of, okay? So this was the basic colligative property that we did yesterday. So basically in previous lecture we have discussed two very important concepts, that is relative lowering in vapor pressure and elevation in boiling point, okay? So in today's lecture we will be focusing on depression in freezing point, okay? Now before entering into the freezing point or depression in freezing point property, now let us first understand what basically freezing it, what happens during the freezing and how the mechanism of freezing is happening, okay? So we know that whenever we want to freeze something, okay, you might have seen in your home also, especially in refrigerator, so there is some low temperature, okay, that is maintained inside the freezer, okay, where you put water, it gets frozen. So that is how it is working. So what happens is when we have decreased the temperature, so whenever we want to freeze something, we have to decrease the temperature. Now when we decrease the temperature, the kinetic energy of the molecules would decrease, okay, because we know that the average kinetic energy of molecules is directly proportional to the absolute temperature, okay. So when we are decreasing the temperature, so we are decreasing the kinetic energy of the molecule. So what was initially happening, the molecule was moving rapidly here and there, colliding with each other. Now when we have suddenly lowered the temperature, the motion of the molecule will cease and they will start moving very slowly, okay. Now when they start moving very slowly, what would happen, the intermolecular forces of attraction between the molecules would come into play, okay, because now they are moving very slowly. So this intermolecular force of attraction will come into play and they will come closer to each other, okay, and the interactions would lead the molecules to come in the pattern in which they can form a solid. So that's how the freezing mechanism happens, okay. So if you look at the statement, it says that when a substance starts to freeze, okay, the molecules slow down due to decrease in kinetic energy, okay, because we have decreased the kinetic energy by lowering the temperature. So we will say that the molecules have slowed down now due to decrease in temperature. And when the temperature decreases, the intermolecular, when the molecule slows down, the intermolecular forces of attraction starts to take over, okay. Then molecules will arrange themselves in a pattern and thus turns into a solid. So this is the way exactly how a liquid changes into solid when we keep on decreasing the temperature, okay. So if you look at the definition of freezing point, now till now what we were saying that freezing point is basically the temperature where the liquid is getting converted into solid. So the temperature at which a liquid is getting converted into solid is called as freezing point. But like the exact definition of freezing point is not that. Freezing point is the temperature at which the vapor pressure of the solid and the liquid becomes same. Okay, so suppose you are freezing water. So when you have started freezing water, water will have some vapor pressure. Okay, similarly, the ice, that is the solid, will also have some vapor pressure. Now this is little confusing because we have said that liquid particles can easily move out of the solution because the intermolecular forces of attraction between them is less. Okay, so they can easily come out. Okay, so they can easily come out. So we say that liquids generally have vapor pressure. But if you look at the solid, in solid the particles are closely binded to each other. So we must be thinking that if you leave any solid in the room, you cannot see the vapor, okay, no vapor is formed, okay, because the composition of that solid is not changing. But there is some vapor pressure that is exerted by solids also. Some solid particles will also go into the vapor phase, okay, but it generally happens at very low temperature, okay. So basically freezing point is the temperature at which the vapor pressure of the solid and that of the liquid becomes equal, okay. So this is a very important definition, so you can note it down. It is the temperature at which vapor pressure of both liquid and solid of a solvent becomes same, okay. So now let us consider the text of depression in freezing point. So we have already, with this as a fact, we already know that whenever we are taking a solvent will have some vapor pressure, okay, it is a pure solvent, so it will exert a vapor pressure that is equal to P naught. P naught is the vapor pressure of the pure solvent. Now when we mix a non-volatile solute to it, now it is apparent that upon addition of non-volatile solute to a solvent, the vapor pressure would decrease, okay. Now what happens when the vapor pressure decreases? We know that because the vapor pressure has decreased, so to boil that solution, we need to give more heat so that more vapor would be formed and the vapor pressure would become equal to the atmospheric pressure, that is 1 atm, that is called as, then the temperature is called as the normal boiling point, okay. So we say that when we are adding a non-volatile solute to a volatile solvent, so there is always an elevation in the boiling point, okay. Now the important concept which is over here is, now when we are adding a non-volatile solute to a solvent, so we are saying that its freezing point is decreasing. Now let us see how it is decreasing and let us understand the mechanism or the process through which the depression is happening. So we know that when we have taken a solvent and we have added a non-volatile solute, so basically the vapor pressure of the solution would decrease, okay, because the solute particle will also occupy the surface and the number of solvent particles that are escaping out into the surrounding, okay, as vapor would decrease. So that's why the vapor pressure decreases. Now we know that freezing point is the temperature at which the vapor pressure of solid and liquid becomes equal. Now because the vapor pressure has decreased, okay, so the vapor pressure has decreased. So for freezing to happen, we know that the vapor pressure of liquid and solid should be same. Now because there is a decrease in the vapor pressure, okay, so somehow we need to increase the vapor pressure. If the vapor pressure increases, then it would become equal to the solid and then the solution would start freezing. So what happens? We lower the temperature, okay. So at a particular temperature, suppose the solvent was forming a solid, okay, suppose we are considering water. So water, when we are taking it to 0 degree Celsius, it was forming a ice. Now, when you added a non-volatile solute at that temperature, suppose you have added at 0 degree Celsius, you have added some non-volatile solute, say salt. Okay, now some of the ice melts. Okay, now some of the ice melts. So what happens at that point when we are saying that when we have added a non-volatile solute, the vapor pressure of the liquid has decreased. So for the system to solidify, for the system to change into a solid state, okay, we need to increase the vapor pressure of the liquid. Okay, now when we have added the non-volatile solute, vapor pressure will always decrease. So vapor pressure will only increase when some of these solids or when some of the ice that is formed in the solution starts melting. Okay, because if this ice that is formed inside the solution starts melting, we will get more component in the liquid phase. Okay, the solvent will come in the liquid phase. Now because the solvent is in liquid state, okay, the more number of water molecule would be in liquid state, and according to Raoult's law, if the component is more in the liquid state, then it can form more vapor. Okay, so what would happen now when we have added a non-volatile solute? So the vapor pressure has decreased. Now the vapor pressure of the liquid should increase, then only it will become equal to the vapor pressure of the solid, then only the freezing would start. So at that point, some amount of ice or some amount of solid of the solvent that has formed would start melting. Now when it melts, it will enter into the liquid phase. So the number of molecules in the liquid phase of the solvent would increase, and hence the number of molecules of the liquid at the surface would also increase. That would result into the more vapor pressure. So when we are adding a non-volatile solute, the vapor pressure goes down. So to increase the vapor pressure, more solid has to melt. On melting, more liquid will be formed, more number of solvent molecules would be there in the liquid phase. So the number of molecules of the liquid phase at the surface would increase. That's how the vapor pressure can increase. So we say that whenever we are adding a non-volatile solute to a volatile, to any solvent, the vapor pressure has decreased, and at that point some of the solid that was already formed by freezing would start melting, okay, and more number of liquid particle would be generated, due to which more number of liquid particle can go out as vapor, due to which the vapor pressure will become equal and the solution can freeze. So what happened exactly over here is, we had a water at 0 degree Celsius. Okay, so we know that water, suppose there was an equilibrium established, we have taken water at 0 degree Celsius, some amount of ice has been formed in the solution, okay, some amount of ice has been formed in the solution and some water exists. Okay, so it is basically a ice water equilibrium. Now in this equilibrium we have added some salt. Now as soon as you add the salt, more amount of ice will start melting. Okay, so more amount of ice will start melting. Hope this is clear now. So as more amount of ice starts melting, so it becomes very clear that at that particular temperature the solution won't freeze. Okay, so what we have to do, we have to decrease the temperature even further so that the solution starts freezing. So that's where the depression in freezing point comes. Okay, so if you look at, suppose we are having a solvent, suppose we are having water, okay, at 0 degree Celsius, and some ice is also formed. So this is the ice cube. Okay, so ice cube is also formed. Okay, so there is an equilibrium between ice and water. Now when we add non-volatile solute, what I am saying is the vapor pressure of the solution would decrease. Okay, initially this system was at 0 degree Celsius, so it means that the vapor pressure of the solid and liquid were same of water. Okay, now when we have added non-volatile solute, suddenly the vapor pressure of the liquid would decrease. Okay, now the vapor pressure has decreased. So what would happen to increase the vapor pressure again, because there was an equilibrium established between ice and water. Okay, on addition of non-volatile solute, the vapor pressure decreases. So to increase the vapor pressure again, some amount of ice has to melt. Okay, on melting what will happen? It will create more number of solvent particles. Now because the number of solvent particle increases, so the chances of occupying the surface also increases. So the number of particles at the surface would increase, due to which more number of water can escape as vapor. Okay, due to which it will have more vapor pressure. So when you have added non-volatile solute, so this solution will start melting, the ice will start melting. That means at that temperature, that is at 0 degree Celsius, now the solution won't freeze. Okay, so we have to even lower the temperature. We have to go in some minus, say -2 or -3 degree Celsius. Then only the again solidification process will start. So upon addition of non-volatile solute, we are saying that freezing point decreases. Okay, now this depression in freezing point is proportional to the amount of non-volatile solute you are adding. Okay, more is the number of solute particle. Okay, what would happen if you have added more amount of solute to this? So the vapor pressure of the solution would decrease to a greater extent. So more amount of this ice has to melt, so that more number of water molecule will go outside as vapor. Okay, and the vapor pressure of liquid would become equal to that of solid. Okay, so in that case we will say that more is the amount of non-volatile solute that is added, more would be the depression in freezing point. Now because this property again depends upon the amount of solute particles rather than nature of the solute particle, that way this is also a colligative property. Okay, so if we check this on graph, so this is the basic line. Okay, so this represents the pure liquid solvent. Okay, this graph, like this is just a estimation. The exact graph comes from the exact graph is something like this. Okay, so we have just extrapolated it. So this extrapolation does not have any significance. So this is of that of pure solid solvent. This is pure solvent. Okay, and this is of that of solution. Okay, so you can see that at a particular pressure, the freezing point initially was this, the freezing point finally became this, so there is a depression in freezing point. Okay, hope this is clear to you. I will read all this if the image is not clear. So we are saying that if we look in the phase diagram, okay, the pressure versus temperature graph, so we say this is for the pure solvent. Okay, and this would be the vapor of solution. Okay, so I will write it with red so that you can clearly see that at any temperature the vapor pressure of pure solvent is more. So suppose this is your 1 atm. Okay, so this would correspond to the freezing point of pure solvent. Okay, and this would correspond to the freezing point of the solution. So you can clearly see that there is a depression in freezing point. Okay, so we'll write depression in freezing point as, okay, depression in freezing point is freezing point of the pure solvent. Okay, because that is having a greater value minus freezing point of the solution. So this is your written as delta TF. Now we have already defined if we add more number of solute particles in the given solvent, the vapor pressure of the solution would keep on decreasing. Okay, so more is the number of particle added, the decrease in vapor pressure would be more. So to increase the vapor pressure again so that it becomes equal and the solid starts forming, so what we have to do, we have to melt some amount of ice that is formed over there. So basically the ice will melt, some amount of ice will melt and it will come out as vapor, so that the vapor pressure becomes equal. So we know that it is a colligative property. So this also depends upon the molality of the solution, just like the way we are doing for boiling point elevation. So if you remove the proportional sign, so we get a constant which is Kf in this case. Okay, so if you look at the formula, it is almost same as that of the elevation in boiling point. So m over here is the molality. Kf is known as cryoscopic constant. Okay, it is called as cryoscopic constant or freezing point depression constant. Okay, hope this is clear to you, and delta TF is the depression. So if you look at the definition of Kf, we will say that when the molality is 1, so the depression in freezing point is also equal to the molar depression constant. So we will say that Kf is equal to depression in freezing point for a 1 molar solution. Okay, for a 1 molar solution. Okay, so if you look at the unit of this, so unit of this would be Kelvin, kg, okay, Kelvin, Kelvin kg per mole. Okay. Again, the value of Kf would be a constant for a particular solvent. So this is constant for a particular solvent. So if you change the solvent, the value of Kf would also change. So if suppose we are changing the solvent, then the depression in freezing point of a substance would keep on changing. If we are adding the same non-volatile solute in different solvents, okay, different solvent means suppose we are adding a non-volatile solute in water, or suppose we are adding it in benzene. So the depression in freezing point for the same strength of the solution would be different, because the value of Kf is different, because even if molality of both the solutions is same, the value of Kf is different. So delta Tf or the depression in freezing point is always different. Okay, so this is the basic unit. Okay, so if you look at this, we can, like the way we did in elevation in boiling point, so Kf is basically R into Tf square into molar mass of solvent divided by 1000 into latent heat of fusion. Okay, so this is RTF square. R is basically your gas constant. It's on the similar line as that of Kb. Okay, so Tf is your freezing point of solvent. Okay, capital M I have already told you, when solvent we are writing, it means it is molar mass of the solvent. Okay, and delta H fusion is enthalpy of fusion. Okay, hope this is clear to you. Or we can also write this as Kf equals to R Tf square upon 1000 into LF. LF is basically latent heat of fusion. Okay, so LF over here is latent heat of fusion. Okay, so when we are adding a non-volatile solute to any solvent, the boiling point of that solvent would increase now, okay, and the freezing point of that solvent would decrease, okay, because vapor pressure decreases. Okay, so to increase the vapor pressure, again the solid that had been formed in the solution has to melt, then only the vapor pressure can increase. There is no other way the vapor pressure could increase. So the solution at that temperature would start melting. So the solution which froze at initial temperature, upon addition of a non-volatile solute, won't freeze. So it will start melting. So we have to lower the temperature so that the solution remains in a frozen form. Okay, hope this is clear to you. So there are two ways to find the value of depression in freezing point. One is your, again, known as Rast process. Okay, so basically what happens in Rast process, okay, so there are two ways to determine delta Tf experimentally. So there are two methods. One is known as Rast method. So what happens in Rast method, we take any unknown compound, unknown solute, okay, and we dissolve it in camphor as a solvent. So in this process we are taking camphor as the solvent. Now what is the use of taking camphor as the solvent, camphor generally has a very high value of, okay, or a very large value of Kf. Okay, so if Kf value is large, so even if the solution is very dilute, okay, so even if the solution is very dilute, that means the value of M would be very less, because if the solution is dilute, it means that the number of solute particles is less. So if the number of solute particle is less, so obviously its molarity would also be less, because molarity is number of moles of solute upon mass of solvent in kg. Okay. So if we are saying that if we take a dilute solution, okay, its mole fraction, its molality would be very less. Okay. Now because the value of Kf is very large, so delta Tf is equal to Kf into M. Because the value of Kf is very large and the value of molality is very small, if you multiply them, you will again get a significant figure, okay, that can be easily recorded through a thermometer. Okay. So that's why Rasch process is very useful. Okay. In Rasch process we can find the molar mass of any unknown solvent. Okay. Because suppose we want to find the molar mass of unknown solvent, so what we'll do, because we don't know the mass of it, so what we'll do, we'll take a very small amount of it. Okay, because we don't know the molar mass, so we don't know if the solution we are preparing is very highly concentrated or highly dilute. Okay, because we don't know the molar mass. So what we'll do, we'll take a very, we'll form a very dilute solution of that particular unknown organic compound. Okay, we'll dissolve in the camphor solvent and then we'll lower the temperature. Okay, we'll record the temperature at which the solution freezes. We knew the initial freezing point of camphor, so we'll get the depression in freezing point, okay, that is equal to Kf into M. So we know the value of Kf, okay. So from that we can get the value of molar mass of the unknown compound as well, okay. But this method is basically used to determine delta Tf experimentally, because if the solution is very dilute, because the value of Kf is very large, when you multiply them, still we'll get a figure, still we'll get a number which is higher, okay, which can be easily recorded in the lab, okay. The second is your Beckmann's method. Beckmann's method is basically based on a Beckmann's thermometer. Beckmann's thermometer has been calibrated to find the very small temperature changes as well. So these are the two methods through which delta Tf can be determined experimentally. One is Rasch process. In Rasch process, camphor solvent is used because it has a very large value of Kf. Okay. Even if the solution is very dilute, the product of Kf into molality would be still large enough to record it in lab very easily. Okay. And the second is Beckmann's method. So this is your basic concept of depression in freezing point. Okay. So we can just solve this question now. Just read this question once. So this says that we are having an aqueous solution of a non-volatile solute which boils at 100.17 degrees Celsius. So we know that the boiling point of this solution is 100.17 degrees Celsius. At what temperature will the solution freeze? Kb for water has been given to us and Kf for water has been given to us. So we know that the boiling point of pure water at 1 atm is 100 degrees Celsius. Okay, now when we have added the non-volatile solute, the boiling point of the solution became, okay, so the boiling point of the solution became 100.17 degrees Celsius. So the elevation in boiling point we know is 0.17 degrees Celsius. Okay. Now we also know that the elevation in boiling point is equal to m into Kb. Okay. So this is 0.17. Kb for water we know is 0.512 into molality. Okay. Now let us look at the freezing point data. It is asking at what temperature will the solution freeze. So we know that the freezing point of pure water is 0 degrees Celsius. You can also write in Kelvin, there is no issue in this. So this is 0 degrees Celsius. So we want to find out the freezing point of the solution. Okay, we know that the depression in freezing point is Kf into m. Okay, so we don't know the value of m, so m can be calculated from here. So delta Tf, I can write this as Kf is 1.86, m I can write as 0.17 upon 0.512. Okay, so this is how I will get the freezing point of depression in freezing point. So we know that depression in freezing point is freezing point of pure water. Okay, so freezing point of pure water minus freezing point of the solution. This is equal to 1.86 into 0.17 upon 0.512. So we know that the freezing point of water is 0 degree Celsius. Okay, so delta TF of the solution, freezing point of the solution would become minus 1.86 into 0.17 divided by 0.512. Okay, so this answer is in degree Celsius. You can add 273 to this and you will get the value in kelvins. Okay, so this is how you solve this question. You can take a snapshot of the question. That would actually help you when you are making your notes. You can see the questions that we have solved. Okay, so this is again a very basic question. So just read this question. I will just make some way to make you read this. So this says that 1.4 gram of acetone dissolved in 100 gram of benzene gave a solution which freezes at 277.12 Kelvin. Pure benzene freezes at 278.4 Kelvin. 2.8 gram of solid A is dissolved in 100 gram of benzene which froze at 277.6 Kelvin. So we need to calculate the molar mass of the unknown solute A. Okay. So just look at the question, just try to solve it. I will give you 2 minutes to attempt this. Okay, I hope you have a pen and a paper with you and you are attempting the question. So initially a data has been given to us. We know that the freezing point of pure benzene is 278.4 Kelvin. Okay. Now the freezing point of the solution is given as 277.12 Kelvin. Okay. So the depression in freezing point would be pure solid minus solution. So you can calculate this. So this is 1.28 Kelvin. Okay. So we'll say that delta TF is equal to KF into M. Okay. Now this initial data is given to calculate the value of KF because nowhere you can see that KF of the solvent benzene is written over here. So we know that molality is acetone, we know is CH3 C double bond O CH3. So if you know the molar mass of this would be, there are 3 carbon, so 36, 6 hydrogen, 42 and 1 oxygen. So that contributes 16 to the molar mass. So the molar mass is 58. So we can write the number of moles of acetone as 1.4 upon 58. Okay. So molality is number of moles of solute 1.4 upon 58 divided by mass of solvent in kg. So solvent we can see is benzene. So mass of solvent in kg would be 0.1. So we'll get the value of KF as 1.26 into 0.1 into 58 divided by 1.4. So we'll get the value of KF from here. So this we have to use in the second part of the question, which says that we have now dissolved some unknown solid A in benzene, in the same 100 gram benzene, and we got a freezing point of 277.6 Kelvin. Okay. So now we'll say that the freezing point of the solution is 277.6 Kelvin. Freezing point of the pure benzene was 278.4 Kelvin. Okay, so we'll say that depression in freezing point is that of 0.8. Okay, so depression freezing point is 0.8. So we know that delta TF is equal to KF. The value of KF we know is 1.26 into 0.1 into 58 divided by 1.4. Okay, delta TF is KF into M. Now M over here would be molality of this solution. So molality of this solution would be number of moles of solute. Number of moles is mass upon molar mass. Let the molar mass of the unknown solid be M divided by mass of solvent in kg, which is 0.1. Okay, so from here we can get the value of M. So 0.1 will get cancelled out. So we will have 1.26 into 0.1 into 58 into 2.8 divided by 1.4 into 0.8. Okay, so you can just see, it's again a little calculative question, but it is simple. Okay, so we have just cancelled out 0.1, 0.1, so this term won't be there. Okay, we have cancelled this 0.1 with 0.1, so 1.26 into 58 into 2.8 divided by 1.4 into 0.8. So you can calculate this, you will get the answer. Okay. Okay, so hope this is clear to everyone. So in this question, the first data, okay, this data was given to us because everything was known over here. We knew the mass of acetone, we knew the molar mass, we knew the mass of benzene or the solvent in kg. We also know the freezing point of the solution and freezing point of the pure solvent. So from this data, we can find out the value of the cryoscopic constant or the molar depression constant or the depression elevation depression in freezing point constant. Okay, so we'll get that, okay, by using the equation, and then we'll plug this value of Kf because the value, the solvent, every solvent has a different value of Kf because the solvent remains the same in the second part. So we'll use this value of Kf, okay, and we'll get the molality, and through molality we'll get the number of moles. From number of moles we'll get the molar mass of the unknown, okay, solute A. Okay, hope this is clear to everyone. Okay, so okay, just try this question. This is a good question. Just read the question. I will make you understand what we have to do in this one. So this says that calculate the amount of ice that will separate out on cooling a solution containing 50 gram of ethylene glycol in 200 gram of water. Okay, so everyone must know the formula of ethylene glycol, which is this CH2H CH2H. So the molar mass of this would be, there are 2 carbons, so this is basically 24, 2 oxygen, so that is 32, okay, that is 56, 6 hydrogen, so the molar mass would be 62 gram per mole. Okay, so this says that we have dissolved 50 gram of ethylene glycol in water and we have lowered the temperature to minus 9.3 degrees Celsius, and the question is asking what would be the mass of water, what will be the mass of ice that will separate out. Okay, so Kf data has been given to us. Okay, so first let me just check. Okay, first what we'll do, what we are doing, just forget about this data minus 9.3 degrees Celsius. What we are doing, we are taking 50 gram of ethylene glycol and we are dissolving it in 200 gram of water. So let us check the freezing point of this solution when 50 gram of ethylene glycol is added to 200 gram of water. Okay, so the number of moles of ethylene glycol would be 50 upon 62. Okay, the molality of this solution would be number of moles of ethylene glycol divided by mass of solvent in kg. Okay, so the mass of solvent in kg would become 0.2, so this would be 50 upon 62 into 0.2. Okay, so this I can write as 250 upon 62. Okay, so the depression in freezing point when 52 grams of ethylene glycol is added to 200 gram of water would be delta TF would be Kf into M. Okay, now you have to calculate this. You have to calculate this data. Okay, so this is 7.5. So you can see that the depression in freezing point is 7.5. That means the depression freezing point is the freezing point of pure water, which is 0 degree Celsius, minus depression freezing point of the solution. This is equal to 7.5. So depression in the freezing point of the solution would be minus 7.5 degrees Celsius. Okay, so when we add 50 gram of ethylene glycol in 200 gram of water, the freezing point of that solution is minus 7.5 degrees Celsius. Okay, I hope this data is clear to you. So we are basically finding, okay, We have taken the system that in 200 gram of water we are adding 50 gram of ethylene glycol. So we are just checking what is the freezing point of this solution. Now we can clearly see that we have lowered the temperature, okay, which is below its freezing point. Okay, so we have lowered the temperature below its freezing point. So now it is very clear that some amount of water would definitely solidify, some water would change into ice. Okay, so this data is also very clear to us now, because the freezing point of the solution is minus 7.5 degrees Celsius and we have like decreased the temperature to minus 9.3 degrees Celsius. So we are below its freezing point. So some amount of water would again solidify and would separate as ice. So that's what we have to calculate over here. Okay. So what we are going to do is, when the temperature becomes 9.3, minus 9.3, we'll find out the molality of the solution at that point. Okay. So we will say that the depression in freezing point, okay, suppose we have frozen the solution to minus 9.3 degrees Celsius. So the freezing point of water was 0. Okay. Now we have taken the temperature to 9.3, minus 9.3. So depression in freezing point would become 9.3. So this would be equal to Kf, which is 1.86 into m. Okay. So we'll get the value of molality, which is 9.3 upon 1.86. Hope this is clear to you. Okay. Now when the solution started to freeze, when some amount of water started to freeze into ice, okay, so we have to just look at the molality. Okay, now we know that molality is number of moles of solute, okay, because a solute never freezes in the solution. It is only the solvent that is freezing in the solution. So again a question can come on this as well. So what is happening basically, during freezing only the liquid solvent is getting converted into solid solvent. So the equilibrium is always between, okay, so the equilibrium is always between the liquid and the solid solvent. Okay, so we say that the non-volatile solute does not generally go into the solid. Okay, at this temperature, first all the liquid will, or first all the solvent will go, then only solute will go. So at this temperature, we will say that there is an equilibrium between the liquid solvent and the solid solvent. So water in the solvent is changing into water ice or water solid. Okay, solute remains in the solution. So the number of moles of solute remains in the solution. Okay, so we will say that molality is number of moles of solute, which is 52. Okay, sorry, which is 50 upon 62. Okay, divided by mass of solvent in kg. Now we don't know the mass of solvent over here. Okay, so because some amount of liquid solvent has already converted into ice, so we don't know the value of that mass. Okay, mass of solvent in kg, that mass of solvent we have to take it of liquid only. Okay, because we are forming a liquid solution. So because the solution has frozen, some amount of water has changed into solid, so we don't know the mass of the liquid. So we will calculate the mass of solvent or mass of water, okay, in the solution at 9.3 degrees Celsius. So this would be 50 into 1.86 divided by 9.3. Okay, sorry, this is, so mass of solvent, okay, this would be 1.86 into 50 divided by 9.3 into 62. Okay, you can clearly see this is, if you cut this, this is 0.2. Okay, so this is 10. So this is 10 upon 62. Okay, so we have to just calculate this. So I will just calculate with calculator. So 10 upon 62. So this is 161. Okay, 0.161 kg. Okay, so we will say that the mass of water in the final solution is 161.2 grams. Okay, so the mass of ice that would be separated would be 200 minus 161.2 grams. Okay, hope this is clear to you now. So I will just repeat this. This is again a very good question. So this says that we have taken 50 gram of ethylene glycol dissolved in water, 200 gram of water, and we have lowered the temperature to minus 9.3 degrees Celsius. They are asking that what would be the amount of ice that would be separated out. So first what we will do, I will just first, out of my inquisitive nature, I am just first checking that what is the temperature at which this solution will freeze. So 50 gram of ethylene glycol in 200 gram of water would freeze at minus 7.5 degrees Celsius. So I am just using the basic formula delta Tf is equals to Kf into m. Okay, I know the value of Kf, I know the value of m. Now it is clear that we are going below its freezing point. So obviously some solvent would freeze out. Okay, so they will change into ice and they will go out of the solution. Okay, so we need to find the mass of water at that temperature. So we will say that if we have lowered the temperature to minus 9.3 degrees Celsius, so the depression in the freezing point would be 9.3. So at this temperature we will find the molality. Molality came out to be this. Now molality we know is number of moles of solute upon mass of solvent in kg, because in this question it is clearly written that ice is separating out. That means solvent is going from liquid to solid phase, but the solute is remaining in the solution only. So the number of moles of solute remains the same. So molality is number of moles of solute, which is 50 upon 62 divided by mass of solvent in kg. So this is basically this quantity. Okay, so if you calculate the mass of water, okay, this basically is mass of water in solution. This would come out to be 1.161 kg or 161.2 grams. Okay, so mass of water that is there in the solution is 161.2. So the mass of, initially the mass of water was 200. So remaining water has converted into ice. Okay, so this is again a very beautiful question, a good conceptual driven question. I hope you have understood this question. So we generally say that whenever there is a, okay, so you have to remember this also, whenever there is a freezing, okay, when we have added a non-volatile solute to a solvent, so we will say that there is a equilibrium between the liquid solvent and the solid solvent at the equilibrium. There is no solute over here. Okay, hope this is clear to everyone. You can take a snapshot of this and can attempt again. Okay, so just read this question and try to solve this. This is based on these similar lines. Okay, like the way we have solved the previous question, but you have to understand what this question is asking. So it's just a modification of that question. Okay, so just have a look at this question. So this says that a 10 molar solution of urea is cooled to minus 13.0 degrees Celsius. What amount of urea will separate out if the mass of solution taken is 100 gram? Okay, so just try to attempt it now. Okay, so I hope the question is clear to you. So we are having a 10 molar solution of urea which is cooled to minus 13.02 degrees Celsius. What amount of urea will separate out? So in this question, urea is getting separated out if the mass of the solution taken is 100 gram. So here we have to consider that the solute is getting separated out. Okay, so we'll just analyze the data first. Okay, so nothing has been given to us. So we know that initially the solution was 10 molar. Okay, initially the solution was 10 molar and the total mass of the solution was 100 gram. Okay, so let the mass of urea be x gram. Okay, so we know the molar mass of urea. Okay, urea is basically NH2 CONH2. Okay, so this is basically 14 plus 14 28, 28 plus 12 40, 16 56 and 4 60. So the molar mass is 60 gram per mole. Okay, so the mass of water, okay, in the solution would be 100 minus x, because the total mass of the, okay, the total mass of the solution was 100. Okay, so we know that the initial molality was 10, so we can find out the value of x. So 10 would be equal to x by 60, number of moles of solute, okay, upon the mass of solvent in kg. So mass of solvent in kg would be 100 minus x into 10 raised to minus 3. Okay, so if you can just do the calculation, so this would become 100 minus x, okay, into 60, this will be equal to 1000x. Okay, just we are doing the basic mathematical calculation. So this is basically 6000 equal to 1060 x. So we can find out the value of x. Okay, so this would be the mass of solute taken initially. Okay, so this would be the mass of urea in the 10 molar solution. Okay, so we have assumed the mass of the urea, okay, as x gram. Molar mass of urea was 60, so the number of moles of urea would be x upon 60. Okay, so the mass of water in the solution would be 100 minus x, and in kg we can write it as 100 minus x into 10 raised to minus 3. Okay, so molality was given as 10, so we are just taking this over here. So okay. So there is a 10 over here. I have missed that. So this would be, okay, 60,000. Okay, just let me change this. Okay, so this is basically 1000, okay, into 60. So this would be minus 600x equals to 1000x. So x would be 60,000 upon 1600. Okay, so this would be 600 upon 16. Okay, so this would be the mass of the urea initially. Okay, now what we are doing, we have cooled this solution to 13.02 degrees Celsius. Okay, so when we have cooled it to 13.02 degrees Celsius, we need to understand what is the molality at that particular temperature of the solution. So we know that delta TF would become 13.02. Okay, so this is equal to KF, which is 1.86 into m. Okay, so if you do the calculation, I think this should come out as 7. Okay, so let me check it. So this comes out to be 7. Okay, so the molality comes out to be 7. So the solution which was initially having a 10 molar, okay, when we freeze the solution to minus 13.02 degrees Celsius, the molality became 7. Okay, so the molality is decreasing. Now the molality can decrease either when the mass of, okay, when the mass of solute is decreasing, okay, because molality is number of moles upon number of moles of solute upon mass of solvent in kg. So mass we know is 7, molality we know is 7 molar. Okay, hope this is clear to you, because when we are freezing the solution, if solvent is getting separated as solid, as in the previous case, you can look at this. Okay, so initially in this question we said that water is changing into ice, so solvent is changing into ice. So we can understand the mass of the solvent in the solution is decreasing. Okay, mass of the solvent in the solution is decreasing. So because mass is decreasing, so the molality in that case would increase. Okay, so when the solution is getting like when we are freezing the solution, so the molality of the solution keeps on changing. Okay, so if the water is getting separated out as ice, so the molality of the solution keeps on increasing. Okay, but in this case the molality has decreased. It means that mass of solute has decreased. That means solute has passed into the solid phase. Okay, so now we know that the molality is 7. So molality is number of moles of solute. Okay, so let the mass of solute in this final solution be y. So moles would be y upon 60 divided by total solution was 100 grams. Okay, so we can say that at that point the mass of solvent in kg would be this. Okay, y is the mass of solute, okay, at this molality. So the mass of solvent would be 100 minus y, because total mass of the solution is 100 only. So we can calculate the value of y from here. Okay, so y will be the final mass of solute that is present when the temperature was 13.02. Now we knew the mass of the initial, okay, solute that we had taken. So we just subtract x minus y, we get the value. Okay, hope this is clear to you. So a very important point to be understood. Now a conceptual question can come like this. Suppose we are having water. Okay, now we have added some solute to it. Now will this have a range of temperature of freezing, or the entire solution will freeze at one particular temperature. Okay, so if you keep on lowering the temperature, now initially because water was there, so the solution would freeze at 0 degrees Celsius. Now when you started lowering the temperature, okay, when you started lowering the temperature, so the solution would freeze below its freezing point because we have added a non-volatile solute. So suppose at a particular temperature, the solution starts to freeze. Okay, so when the solution starts to freeze, some amount of solvent will go into solid phase. Okay, water will change into ice. So the mass of solvent would decrease in the solution because mass of the solvent has decreased. So molality, which was number of moles upon mass, okay, that would increase. Okay, now because just when the freezing started, molality of the solution increased, so the depression in freezing point would become even more. Okay, so that at that particular concentration, the freezing point would again depress. Okay, so we have to again like lower more temperature to get more solid. Okay, now when we lower more temperature, we get some more amount of solid, the molality of the solution will again increase. Okay, so the depression freezing point will again increase. So we have to keep on decreasing the temperature till we get the entire solution as a solid. Okay, so that is the idea behind this. So when you do the required calculation, you can clearly see that when we were cooling the solution to 13.02 degrees Celsius, the molality decreased. Okay, now the molality decreased, it means that the mass of solute is decreasing and solvent is not decreasing, because if the mass of solvent is decreasing, we know that molality is number of moles upon mass of solvent in kg. Okay, so if the solution is freezing, if the solvent is freezing, so the mass of the solvent in liquid phase would decrease, so molality would always increase. But because here molality has decreased, so it means that the solute is okay going into the solid phase. So let the mass of the solute be Y in the final solution. Okay, so we are writing this as number of moles would become Y by 60. Okay, mass of the solution was 100, so the mass of the solvent would be 100 minus Y. Okay, in kg it would be to 10 raised to minus 3. So you can do the calculation, you can get the value of Y. So this would be the mass of solute in the solution at this particular temperature. Okay, and this was the mass of solute initially. So this was the mass of solute initially. Okay, and this would be the mass of solute finally in the solution. So when you subtract them, you will get the mass of solute that is separating out. Okay, so again a very beautiful question, very good conceptual question. Okay, so from this you learn a lot. So while solving a subjective question, the learning that comes is a very good one. So I suggest you to solve such kind of questions. It is there in your daily practice problem sheet. It will be there in many other book also. So just solve to understand the concepts. So that's where the problem solving help. You don't have to solve 1000 number of problems to crack a chapter. Solve only say 100 or 150 questions in a chapter. But all the questions should be something of a good level that touches all the concept, which will help you in understanding the topic very well. Okay. So hope this is clear to you. You can just have a quick look at this. Okay, so you will get the value this in grams, you will get this also in grams. Okay. So now I hope it is understood to you that when we are taking a solvent and we are adding a non-volatile solute, the freezing point of that solvent would decrease. Okay. So if we have added some amount of solute, so the freezing point decreased. Now when we went to that temperature, okay, some amount of water would start freezing. Okay. So when the water started freezing, the molality of the solution instantly will increase. So the freezing point will fall again. Okay. So as soon as some amount of ice is formed, the freezing point of the solution will always keep on decreasing. The freezing point will always depress. Okay. So we'll have a range of temperature where we can freeze a solution. If we go beyond a particular temperature, so all the amount of solution, all the solvent in the solution would freeze. Suppose we took say 10 gram of NaCl in water and we freeze it to say minus 100 degrees Celsius. So at minus 100 degrees Celsius everything will freeze. Okay, so this is again a very beautiful question. So hope you have got this one now. Okay. Okay, so the next concept that we want to study is osmosis. Now most of us has encountered this osmosis term. Okay, osmosis is basically the flow of solvent from one solution to the other through a semi-permeable membrane. Okay, so a very common example is, you might have seen resins at your home. You can take that resin and you just keep in water for a day. Okay, you can see that like after a day you will see that the resin has swollen up. So it means that water, okay, has penetrated into the resin, okay, from its surface. Okay, so this is basically known as osmosis, the flow of solvent molecule from one side to the other side through a membrane. In this case, the coating of the resin was the semi-permeable membrane. Similarly, you can take another example. You take grapes. You know grapes has a lot of water. Like if you press it, the water comes out. Okay, so just keep that grapes in a very concentrated sodium chloride solution. Okay, so when you take the concentrated sodium chloride solution, so it has less amount of water. Okay, now when you add that grape in that particular solution, after one day you will find that the grape has shrink. So what has happened over here? The water inside the grape has moved outside to the solution. Okay, that's why it has shrink. Now it has moved through a membrane. Okay, it has moved through a surface. So that membrane is called as a semi-permeable membrane. So semi-permeable membrane is a membrane which allows only one kind of particle to pass through it. Okay, so semi-permeable membrane is not a membrane which will allow all the kind of particles to pass through it. Generally we say that a semi-permeable membrane allows solvent molecules to pass through it and it blocks the solute particles. So basically osmosis is the flow of solvent across this semi-permeable membrane. Okay, hope this is clear to everyone. So osmosis is defined as the net flow or movement of solvent molecules from a semi-permeable membrane through which solute cannot pass. Okay, so again a very important definition. So this is the flow or movement of solvent molecules through a semi-permeable membrane through which solute molecules cannot pass. If a solution consisting of both solute and solvent molecules is placed on one side of the membrane and the pure solvent is placed on the other side, there is a net flow of solvent into the solution side of the membrane. Okay, so I will explain you this to a particular example. So I hope the definition is clear to you. So osmosis is basically the movement of the solvent particles, okay, from one side to the other through a membrane which is known as semi-permeable membrane. Okay, so I will get to this point. If a solution consisting of both solute and solvent molecules is placed in contact with a pure solvent with a membrane in between, then the net flow of solvent takes place in the solution side. So I will come to this point, don't worry. Okay, so the examples of semi-permeable membrane is, a natural semi-permeable membrane would be animal or vegetable membranes. Okay, and a common example is a pig bladder. Similarly, artificial semi-permeable membrane are those which are artificially made. The common example is copper ferrocyanide. Okay, copper ferrocyanide is basically Cu2 FeCN6, silicates of cobalt, iron or nickel. Okay, so now let me explain what exactly is osmosis and what is osmotic pressure. Okay, so hope this is clear to you. So we have basically defined osmosis as the movement of solvent particles from one side to the other side, from one solution to the other solution through a semi-permeable membrane. Semi-permeable membrane is a membrane which allows only one kind of particle to pass through it. It is allowing only the solvent molecules to pass through it and it is not allowing the solute molecules to pass through it. So it is generally of two types, artificial or natural. Okay, natural is someone that is found in the human bodies or in the nature. So common example is animal and vegetable membrane or pig bladder, and artificial membrane example is copper ferrocyanide, silicates of cobalt, iron or nickel. Okay, so now let me explain this to you. So suppose we are having, okay, a container and in this container suppose it is divided into two segments. Okay, so this is basically our semi-permeable membrane written as SPM. Okay, so we are having a container divided into two portions by a semi-permeable membrane. So we are having, say, a solution over here. Okay, so suppose we are having a solution over here. So this is a solution. Okay, so solution is basically made up of solvent plus solute. Okay, and we are having a solvent over here. Okay, so there are two chambers that are separated by a semi-permeable membrane. Let us call this chamber as A and this chamber is B. Okay, so we have divided the two chamber using a semi-permeable membrane. Okay, so we have divided the two sides with a semi-permeable membrane. Side A has a solution which is having a solvent as well as solute. Side B has solvent over here. Okay, so now we know that osmosis is the movement of solvent particles from one side to the other side through a semi-permeable membrane. Now the next question comes is, from where will the solvent move? Solvent can either move from here to here, from B to A, or the solvent in the solution A can move to B, toward the side B. Now which will move? Okay, so this can be explained on the concept of vapor pressure. So if you look at the vapor pressure that would be developed over the solution. So we know that because there is only solvent over here, so the vapor pressure developed over the solution would be more. Okay, now because suppose there is a solute over here, so the vapor pressure developed over the solution would be less. Okay, we have already done this. Okay, so we know that there would be more pressure at the surface of the solvent as compared to the pressure on the solution. So we know that this is exerting more pressure. Now because the pressure over here is more, vapor pressure is more, so what will happen? The solvent can cross this semi-permeable membrane. Okay, because the pressure over is more, the pressure is less. Because of this pressure, this liquid will move to here. So we'll say that osmosis happens from the first important point, from the region of high vapor pressure to the region of low vapor pressure. So the first point is from region of high vapor pressure. Okay, from a region of Vp is your vapor pressure, from a region of high vapor pressure to a region of low vapor pressure. Okay, hope this is clear to you. So we come to know that solvent, okay, will move from container B into the container A. Okay. Now also we can say that if you look at this, which side has more solvent? Okay, this is a solution over here and this is a solvent over here. So we know that this is pure solvent and this has less amount of solvent. So solvent molecule will move from that region where its amount is more. Okay, so there is basically a gradient, okay, difference in the solvent amount. So solvent will basically move from that side, okay, where there is more solvent, and it will move to the side where there is less solvent. So we say that it moves from region of high concentration of solvent, to a region of low concentration of solvent. Okay, hope this is clear to you. So solvent will always move from the region where it is present in excess amount, and it will go towards the side which is having less amount of solvent. Okay, so we say that osmosis takes place from the region of high wave pressure to a region of low wave pressure, or from the region where the concentration of solvent is more to the region where the solvent concentration is less. Okay. Okay, hope this is clear to you. So just remember, concentration of solvent we are saying, it is not concentration of the solution. Okay, concentration of solution means we are talking about solute. Concentration of solvent we have written, that means from a region of high, okay, density of solvent to a region of low density of solvent. Okay, hope this is clear to you. So this is the basic phenomena of osmosis. Okay, due to the difference in wave pressure, the solvent molecules will move from the region of high wave pressure to a region of low wave pressure. Now next question comes, till what time this solvent will keep on moving? Okay, this solvent will keep on moving to the other side, okay, only when the pressure in the two system becomes same. Okay, now because we know that some water is passing from B to A, so what would happen, this solution would start diluting, okay, more amount of solvent would come over here. Now because more amount of solvent would come over here, the surface will have more number of solvent particles, so the number of particles escaping out would increase, so the vapor pressure would increase. So as the solvent keep on moving over here, the solution becomes dilute and the vapor pressure keeps on increasing. So at the time when the vapor pressure becomes equal to this, okay, the osmosis would stop. Okay, so osmosis would stop when the vapor pressure over the two solution becomes same. So we'll say that osmotic pressure, osmosis would stop. Okay, osmosis would stop if the vapor pressure over the solutions become same. Okay, so we can also say that because vapor pressure is dependent upon the number of moles of solute, okay, we can also say that the concentration has to be equal. So when the concentration becomes equal on both the side, osmosis would stop. So we can also say that osmosis would stop if the vapor pressure over the solution became same or concentration became same. Hope this is clear to you. This is actually very logical, very simple to understand. Okay, hope it is clear to you now. So now let us look at what is exactly osmotic pressure. So again let us just draw that diagram again. So we are saying that we are having, okay, a semi-permeable membrane. Okay, we are having a semi-permeable membrane SPM, which is separating the two compartment. Okay, one is filled with the solution, okay, another is filled with the solvent. Okay, so you can clearly see that only the solvent particles move and the solute never moves. Okay, only the solvent can move through a semi-permeable membrane. Okay, so what will happen? We know that the concentration of solvent is more over here, so the solvent would start passing from the semi-permeable membrane from right to left. Okay, so what would happen? The solvent is coming to this side. So the level of the, so suppose if we like draw something like this. So now when the solvent molecule is coming to this side, so we know that the level of this would keep on increasing, okay, because more and more solvents are moving here. So the height of the solution would keep on rising. Okay, suppose it rose to this maximum height and then suddenly the osmosis stopped. So what would happen? Since this is a height, having a height of h. Okay, so due to osmosis, the solvent molecules will keep on moving from solvent to the solution side. Okay, due to which there would be a rise in the height of the liquid. Now because this liquid is rising, okay, so this would have a hydrostatic pressure. We know that any liquid of height exerts a pressure of h rho g, where rho is the density of the liquid. Okay, so when the solvent is passing from one side to other side, the level of the solution is rising. Okay, so the level of the solution is rising, that means it will exert some hydrostatic pressure. So this h height liquid will exert hydrostatic pressure on the surface of this liquid. Okay. Now when this pressure becomes equal to the pressure through which the solvent molecules are coming, then we'll say that osmosis would stop. So this hydrostatic pressure developed over the solution when the solvent particles are moving from one side to other side is known as osmotic pressure. Okay. So osmotic pressure is basically represented by pi. Okay. So we can write osmotic pressure as H, which is height of the liquid, D, which is density of the liquid, into G. G is the gravity. So this is the hydrostatic pressure that is developed over the solution. So H is height of liquid, D is the density, and G is acceleration due to gravity, density of liquid, acceleration due to gravity. Okay. So when the solvent is moving from one side to other side, so the liquid level will keep on increasing. So this liquid will exert, okay, because this is a column of liquid, so this will exert some pressure on the surface of the solution. Okay. Now in turn this solution will resist the movement of the solution. This pressure would resist the movement of the solvent particle. Now when this solvent particle movement stops, that means the pressure exerted by this solution becomes equal to that exerted by the solvent. Okay. So that pressure is called as the osmotic pressure. So we define osmotic pressure as the hydrostatic pressure developed over the solution. Okay. That is called as osmotic pressure. It is also defined as the pressure applied over the, okay, the pressure applied over the the pressure applied over the solution. Okay, so the pressure applied over the solution. So if we apply this pressure, okay, so this solvent won't cross, okay, so osmosis would stop. So it is also defined as the pressure applied over the solution so as to stop the osmosis. Okay, hope this is clear to you. So osmosis is basically the flow of solvent particles from one side to other side, from the area where there is more concentration of solvent to a region where there is a less concentration of solvent, or from a region of high wave pressure to a region of low wave pressure. Now when this vapor molecule passes from one region to other, okay, the number of solvent particles would keep on increasing. So due to which the height of the solution will keep on increasing, okay, due to which it will exert some hydrostatic pressure on the solution side. Okay. Now if the height is sufficient or the pressure exerted is sufficient so that the solvent is not able to cross the semi-permeable membrane, then that pressure is called as the osmotic pressure. So it is the excessive hydrostatic pressure developed over the solution, okay, is called as osmotic pressure, or we can also define as if we apply this pressure, H rho g pressure on the surface of this liquid, okay, so this solvent won't be able to cross the semi-permeable membrane. Okay, suppose we are not taking the system, we know the value of osmotic pressure. If we apply the same osmotic pressure at the surface of this liquid, so this solvent won't be able to cross the semi-permeable membrane, okay, and osmosis would stop. So this pressure is also known as osmotic pressure. Okay, so the pressure over the solution that can prevent osmosis from happening is called as osmotic pressure. So osmotic pressure is given by C into R into T. It is also equal to H into D into G. H is the height of the column, D is the density of the liquid, G is acceleration due to gravity. Now in this, C is the concentration, okay, T is the temperature, okay, obviously temperature we have to take in Kelvin, and R is your gas constant. Okay, so if you want to find the value of osmotic pressure in atm, then you have to take the value of R as 0.0821. Okay, so you have to just see that you are taking the units correctly. Temperature is always in Kelvin. If concentration you are taking in moles per liter, okay, so molarity, then you have to take the value of gas constant as 0.0821 moles liter atm per mole per Kelvin. Okay, so this is the basic formula of osmotic pressure. Okay, hope you have understood this. This is a very easy concept. Okay, just on the basis of air pressure we are able to explain all the colligative properties. So we have till now we have done 4 important colligative properties, that is relative lowering in vapor pressure. There was a small correction in the previous lecture, so I have made that correction. Hope you have done in your copy as well. Second was elevation in boiling point. Third we did today was depression in freezing point, which solved some 4-5 questions on it, and then we talked about osmotic pressure. Okay, hope this is clear to everyone. You can just write it down quickly. Okay, so this is it for today. We'll do till here only. So today's daily practice problem sheet has been uploaded. Okay, so tomorrow we are going to discuss Van 't Hoff factor. Okay, and we are going to talk about electrolytic solutes. Till now what we are doing, we are taking non-electrolytic solutes. So again a very important session tomorrow. So that is when we are taking a non-electrolytic from a non-electrolytic solute to a electrolytic solute, and after that there would be one lecture in which we will do a lot of problem solving. Okay, whatever concepts we have done, so we will do a lot of problem solving. So if you can see the lecture flow, so in every class I am just trying to discuss at least good 5 to 6 or 7 problems. Okay, so every lecture, every chapter will be basically at least it would have 8 to 10 lectures. So in every chapter we will be solving some 50 questions in the class itself, and that will almost be like 80% of the questions will be of the subjective form. There would be some multiple choice or there would be some comprehension questions as well, but if you are good in your subjective solving and subjective level problem handling, then things become very easy, and then the training becomes very easy. So that's how the mind has to be sharpened, that's how the skill has to be introduced, and then when it is there in you, then we can definitely take off, and then we can definitely do a lot of wonders. Okay, so I hope you understood everything. Okay, you can just go through the questions that we have done today, and if in case you have any doubts, in case you have any issues, just write to us in the chat box. I am waiting from last 1 month that someone will write any doubt in their chat box so that I can discuss with you, but still I think either you are not seeing or either it is very easy for you to understand. Okay, anyways, your feedback is always important to us. So if you are facing any problem anywhere in this process, you can definitely convey to us by calling to us or by writing in the chat box or sending your doubt to us. Okay.